Hi everyone, I'm Abhinav and I have with me my colleague Avi, and today we are going to present distributed file system at Rubrik. So just to give you an idea of the scale, so we protect more than 42 exabytes of data across different offerings, and at this scale you can imagine that we see pretty much different kinds of issues, both in terms of scaling, in terms of data integrity and resilience. So what we are going to do today is to first give you the high-level requirements of this file system. Then we'll go into the design of our file system. We'll deep dive into some of the concepts. And at the end, we'll discuss 2 case studies from the field data related to data integrity. And we'll also discuss what were the challenges and how we solved them. So we want this session to be interactive, so feel free to interrupt us and ask us any questions. So let's start with the basic protection workflow. So let's say you want to protect a VMware object with Rubrik. So the way you do it is by first you configure the vCenter with Rubrik so that all your VMware objects are discoverable. Then you attach an SLA to whatever object you want to protect. Then our periodic job service will pull the data and ingest it into our distributed file system for protection. So these are the common I/O paths. So you can have data coming in from NFS, SMB, iSCSI. Then the data may be moved to a workload-specific ingestion server based on the type of object that you are protecting. Then the data is sent to the formats layer. At formats layer, we compute the incremental. We also do de-duplication, compression, and encryption. And then finally, we persist the data into our distributed file system. So what are the high-level requirements that we want from our file system? So first is that we want to support multiple hardware configuration. So some of our customers use some sort of third-party hardware, which is not qualified by us. So our file system and our whole stack is supposed to work across different kind of hardwares. We also support various platforms like virtual, on-prem, and cloud. We want to use standard POSIX APIs so that our application teams can develop fast. We want horizontal performance scaling because we have clusters that are as small as single node to clusters into hundreds of nodes. And we also want data resilience and integrity. So this is our component design, a very simplified version of our component design. So we have, in a cluster, we have multiple nodes, each running a fixed set of services. The main ones are the job orchestrator, the distributed fuse-based file system, and the metadata service. The fuse-based file system is completely distributed peer-to-peer and masterless, and it uses ext4 to write both data and metadata to the underlying HDDs and SSDs. I'll hand over to my colleague now.
Can you hear me? Yeah, perfect. Yeah, thanks, Abhinav. So now going on to the requirements of the file system. As Abhinav mentioned, data integrity and data resilience are the 2 key requirements from our file system. And we'll be going over how we achieve data integrity using different checksums at different layers to both detect corruptions and also be able to recover from them. Data resilience is important because when we detect a corruption, we need to be able to recover from it. But along with that, we also need to be able to recover from any outages in our cluster. So any nodes going down, bad disks, etc. And we'll be going over what guarantees we want to provide. And in order to maintain this in the background, we need to be able to detect and rebuild any of the corrupted chunks, along with up-replicating any of the lost chunks that happen due to any outages in the cluster, as well as being able to up-replicate for high resilience as customers move to larger and larger clusters and expand their cluster size, which allows for high resilience algorithms to up-replicate data. And with all this movement of data, we need some way of rebalancing the space so that we don't have hotspots that result in higher latencies and slower operations for customers. Along with all of this, another requirement is we need to be up all the time as much as possible, and we can't afford downtime during cluster ops, for example. So we need to have online cluster ops for nodes and disks in order to allow customers to have jobs that run continuously. And another more unique features of our file system is IO prioritization. IO prioritization allows us to take customer priorities or the semantic priorities of jobs, whether it's your threat monitoring, your regular data protection jobs, or your restore jobs at when you actually have a cybersecurity event, and prioritize it at the file system level to give the best latencies possible for each job. In addition, we have some advanced data services. One of the most foremost is the optimal data storage, which essentially means that customers can write to us in different formats, whether it be a write-optimized format, and we can take that format and turn it into a read-optimized format because our file system works usually in a write-once, read-many format. So, and in addition, we also have compression, de-duplication, encryption, which we support natively and can be enabled and disabled as need be. So our file layout is kind of standard. It's kind of similar to what you'd imagine, kind of like Google file system, except obviously we're masterless. And so each file is made up of several fixed size stripes, where each stripe is made up of chunk files that are distributed across different nodes with additional metadata and checksums that are needed to maintain our data integrity and resilience algorithms. And we achieve the resilience part by using different encoding schemes, which can be mirrored, Reed-Solomon, and other forms of erasure encoding. And as you can see here, we showed a very basic mirror 3, but at a very high level, what we want to support for all our customers at the very base level is 1 node, 2 disk, and 1 rack failure tolerance. And most of our failure encoding schemes should be able to support this. So let's look at our file system in depth. So I think Abhinav mentioned that we wanted to expose a simple API, a POSIX API, to all our clients so that they can build on top of us without having to worry about the internal implementation. And Fuse allows us to do that with relatively low latency. But some clients may allow, or some clients may want some extra functionality, and some clients may want to interact directly with our proprietary formats layer. In order to do that, we also have a thrift server, which allows some clients to interact at a deeper level if they need. Abhinav will be going over the proprietary formats later shortly, but this is a layer which actually manages the optimized format, as we mentioned. So allows customers to write in a write-optimized format, and then we transform that data into a read-optimized format for our clients. And underneath that is the chunking layer, which is responsible for allocating the chunks across, maintaining the resilience guarantees that we have, as well as ensuring some level of space homogeneity so that we don't have the hotspots. And underneath all of this is the file server, which receives the data from the chunking layer and actually delegates that I/O down to the disk. But in the middle is the rate limiter and the priority manager. The rate limiter ensures that we maximize the bandwidth of disks, because at different times you may have different windows where you have a burst of I/O and you have a period with no I/O. So we want to be able to, or no or little I/O, obviously. And the rate limiter helps us manage that a bit better. And the priority manager helps us manage the priorities that come from the jobs, as we mentioned, with restores obviously being a super high priority if you have a cybersecurity event, as well as any background jobs such as garbage collection, and allows us to manage the priorities of those and manage the I/Os with respect to that. And underneath the cover, obviously, we have ext4 mounted on top of each of our disks and SSDs. So our basic data integrity requirement was that we needed to ensure data integrity, some level of data integrity on every read, even for small random reads. And so what we do is we have a minimum read size of 4 KB, and we embed an inline checksum in all of our data that is validated on every read at the 4 KB granularity. Now, whenever we do a transformation of a file or up replication or a data integrity recovery, we need to validate that the data is correct after that operation. And we also want to be able to validate some data is correct in the background. And our chunk checksum at our chunk layer, which is usually 32 or 64 MB, allows us to do that. And this is pretty critical to guaranteeing data integrity at a higher layer. In addition, we also have a fingerprint, which is the SHA-1, typically a SHA-1 hash of the logical layer. So our file system usually deals with the physical layer, where you have the chunks and all the 4 KB blocks that we mentioned. But this is at a higher logical layer, which is what the layer that the client writes at. And in addition, we also have end-to-end checksums at higher layers, which we won't go into, but our higher layer jobs and data snappable layer handles this. So some of the additional background operations that we may not have gone over, but just fair to mention, is garbage collection. Obviously, this is something we all need to do. But in a distributed file system, there's always going to be some chances of leaks, and we want to be able to handle that. Another really important part is reporting file system health. Our clients want to be able to know if there is any outage or any corruptions found in the file system, and they want to be able to know how quickly they can recover from it, and that's one of the key parts of our background scan. Another key operation is validating our metadata. We can validate the data all we want, but there still needs to be some sanity checks or safeguards against metadata corruption, and this is the portion that's responsible for that. As we mentioned, we have write-friendly formats, and you need to transform them into the read-friendly format, and compaction is one of the operations, along with several other operations that we won't really go into in much detail, but compaction is one of the operations that helps us achieve this. In addition, we also have global dedupe. As a file system that ingests a lot of data, exabytes of data as we mentioned, we need to be able to have some way of deduping the data over time, especially since customers usually write data in incrementals where there is inherent deduplication in the data, just inherent duplication in the data, sorry. So this is how we actually scan the metadata in the background. So we have our entire metadata can be represented as a bunch of shards, where each shard is composed of directories and files, which each file is containing stripes. And each node is responsible for scanning a particular shard. And once it scans this shard, it can issue IO or take action on the actual data, which can be located on any of the disks on any of the nodes. And as you can see, this is kind of inherently horizontally scalable, and our metadata service is also distributed, which makes sure that our queries are also something that horizontally scales with the size of the cluster. And so what we really care about in terms of performance of our scan is the density of metadata, which is the amount of rows per node, as that is the size of the metadata shard that we care about. And as we mentioned, customers really care about the health of the file system, and we usually are able to report the health of the file system in about half an hour to an hour, which is reasonable enough and allows us to respond to any sort of major outages or cybersecurity events. So we talked about online cluster ops earlier, and we wanted to just provide a very high level of our state machine. So everything starts in active state, but as customers want to either expand their cluster or switch out different hardware, they may want to remove one of the nodes or disks in our cluster, and we move it to a pre-removal state, which is kind of a quiescing state that allows us to drain all the data before we remove the resource from the cluster. And this allows us to ensure that we always maintain that failure tolerance. And even when you do remove something, you're still able to maintain that failure tolerance and not have any additional risk of an outage risking your data. Once you do have a removed resource, there's a hardware discovery phase which kind of mounts, bootstraps the node or disk and ensures that it's all good for us to move back and to take it into active so that the file system can start working on it. But obviously, in addition to remove an actual remove call from the UI or from a manual call from the customer, we may also have hardware errors or ext4 errors. So in the case of a hardware error where we detect a hardware is not functioning as expected or is degraded, we have a system to detect that and move it into failed state, at which a customer can feel free to, we'll notify the customer and they can feel free to remove it at their own pace, but we will be draining some of the data at that point and up-replicating the data, so once we've detected that issue. And for ext4 error, this sometimes is recoverable, and so we do run FSCK to actually attempt to recover the ext4 file system and fix it. If that works all good, we move it back into active state. If it doesn't, we go back into that pre-removal state and we drain the data. But the main kind of idea here is that we always want to be able to ensure that your data is as resilient as possible. And the fact that we continuously try to drain and up-replicate the data whenever we detect an outage proactively helps us ensure this. So I'll hand over to my Abhinav, my colleague, to go over IO priority.
So let's discuss a rather unique feature of our file system, which is IO priority. So let's first try to understand why do we need this. So as my colleague described, so we have several background jobs running in the system, like data rebalancing, data integrity checks, and others. These background jobs are always running. Then we have some SLA-driven jobs like object protection or indexing. And then you can also have a manually triggered job like restore. When there is a cybersecurity event, the customer can manually trigger restore. So you have these three different classes of jobs that are always running, but some are more important than others. And if we don't use the concept of IO priority here, it is possible that maybe background job will take up all of the IOs and the more important jobs will not be able to get the high throughput that we want. So to solve this, we have a few priority classes. We have interactive priority class, SLA priority class, and background priority class. So whenever a job wants to do an IO, so it sets the job context with the file system, and the file system uses that job context to figure out what should be the correct priority class for this particular job. And based on that, the IOs from higher priority jobs throttle the ones from the lower priority jobs. So if we have a interactive priority job like restore running, it will throttle everything, all the other jobs in the system to ensure that interactive priority jobs can run as fast as possible. But that is quite rare. So usually you will have SLA and background priority jobs only. And between these two, we try to prioritize SLA jobs while trying to ensure maximum resource utilization. So let's talk about our data formats layer. So to store periodic backups, our file system supports some advanced data structures. So first is a concept of patch file. So this is a simple key value store similar to SS table that is optimized for on-disk reads. Then we also have something called a fingerprint. So this file contains SHA-1 in 64 kilobyte chunks of the entire logical space. And for each snapshot, we have a fingerprint file. Then we also have journal file, which is a simple log structured file where we just append offset and data. So during the ingest path, we create journal files, which is write optimized. And then in background, we convert it to patch file, which is read optimized. So this is how a patch file chain would look like. So you have snapshot at time t equal to 0, snapshot at time t equals to 1, and snapshot at time t equals to 2. And all of these snapshots point to a patch file in the patch file chain. And all of these patch file just contains the incremental from the last snapshot. So you are ingesting only the minimal data that was changed since the last snapshot, which is contained in the patch file. And along with patch file chain, you also have fingerprint file, which represents the SHA-1 of the entire logical space with each snapshot. So because you have this patch file chain structure, so to actually issue a read, what you have to do is sort of mount a virtual file over it, over this patch file chain. And then if you issue a read to any particular offset, your read may have to traverse down the chain to find the last, the most recent file on which it was written to. So let's see how we can use this fingerprint and patch file to compute incremental diff very easily. So let's say on the right side you have the new physical data of which you want to take a snapshot. On left side you already have a patch file chain. If you mount a virtual MJF over this patch file chain, you would be able to view the full logical view of the snapshot. And as I already mentioned, we have fingerprint file with each snapshot. So we already have the fingerprint, which contains SHA-1 checksums in 64 kilobyte chunks for the last snapshot already. So to compute the incremental with this patch file chain, what we need to do is first we can compute the fingerprint of the new physical data. And then we can just compare these two fingerprint files, and that would give us which data blocks have exactly changed. And then we only ingest those particular data blocks into the journal file, which would be later converted to patch file. So I'll hand over to my colleague now.
Thanks. So I wanted to go over a case study of what we found, one of the cases that we found interesting while investigating an issue among one of our customers. So what we saw was something interesting with regards to sync semantics in ext4 and sync semantics in general. So let's go over a standard client transaction with our file system, which where a client writes to the file system, then a client may do a sync, and then they want to read the data to validate or read the data afterwards. And one thing we want to note is that as most file systems would do, we cannot do a sync after every write in order to be performant. We need to have a sync at some higher layer of granularity, obviously, and we need to balance that with our data resilience guarantees, so keep that in mind as well. So let's go over a client that is issuing a write, say, at offset 12, and is writing foobar to us on node A, and node A redirects this to a file server on node B and writes this to the actual chunk file on node B. And what this write does is it marks the ext4 buffer. It writes to the ext4 buffer, which may not directly be written to disk. And essentially, that ext4 buffer at that time is dirty. So ext4 will flush that data to disk asynchronously, and it can do this according to its algorithms, which may be due to memory pressure or any other heuristics or any of the configs that we set on the cluster. But let's say in this case that ext4 flushes foo to disk asynchronously. And note that the node A is completely unaware of this, and node A has no idea of what has been flushed and what hasn't been flushed. And so as a good client, node A has to sync the data in order to guarantee that the data is actually, the unflushed data is actually persisted to disk. And that ensures that bar is also synced to disk and all the data is on disk, which is great because that means that we are resilient and we are failure tolerant to any failure. And even if the node goes down, we should be able to come back and recover the data by reading the disk. And now when the client issues a read, you should be, we see that there's no dirty data anymore. And the read should return foobar. The read is issued to the disk, read returns foobar. This is all good. And this is what we want to see in our client. This is what we want our client to see, and this is what our transaction should look like. But let's look at what can happen during a crash. So if a client writes the same foobar to offset 12, to file server B, node A, and node A redirects that to file server B. And obviously, the write returns success once we write it to the ext4 buffer. So we have foo and bar in ext4 buffers, and ext4 probably marks this buffer as dirty to flush to disk whenever it wants to. And so ext4, say, flushes foo to the disk asynchronously. And note again that node A is completely unaware of all this. So this is all happening on node B. Now, when ext4, for sake of simplicity, let's say ext4 is flushing bar to disk. And during that asynchronous ext4 flush, node B crashes. At this point, when node B crashes, clearly ext4 can't do anything about this. And the buffers are completely empty. And so all we have right now is foo written to the file. And now if a client on node A syncs, and this node A syncs to file server B, the sync should succeed because there's no data in the buffer to flush. And so the sync will just end up succeeding because there's no data in the buffer at all right now. So you can kind of sense that there's something wrong with this already. But now when a client does end up reading, at offset 12, the read would only return foo because that's what has been persisted to disk, and the buffers that contained a bar has been emptied by the crash. And when we actually saw this, we saw that the behavior doesn't necessarily need to be this clean per se. It's not going to be as simple as a file whose size is necessarily smaller, and you're going to get an EOF or something on the read. It can be anything in between. It doesn't need to be foobar. It can be garbage data. The behavior isn't exactly predictable due to the nature of when the crash can happen and what guarantees or what configurations the particular ext4 file system was mounted with, and the underlying hardware and the firmware as well. So there's definitely different sorts of behavior that you can see in this transaction, but the simplest form would be where you kind of have data loss because you don't even have bar written to disk. So let's look over the potential solutions. So one of the potential solutions would be to keep all your file descriptors in memory at the file server layer. And that would mean that you would be able to have complete knowledge of what file descriptors are active and what your clients are using and what your clients aren't. And this is great because this is simple, it's easy to understand. But obviously, one of the key tenets of our file system is horizontal scalability, and this isn't horizontally scalable. You can imagine if hundreds of nodes are writing to a single file server, the file descriptors would eventually become huge. And in addition, with a lot of file servers, a lot of nodes writing to one file server, and a lot of clients writing to all the nodes, a lot of jobs running on all the nodes at the same time, writing to a single file server, this would mean a burst of I/O would lead to very unpredictable resource usage, where peace times would have very low usage of the file server, and a burst of I/O could lead to very unstable behavior at the file server due to a huge number of file descriptors that are kept in memory. And so what we came up with was some way of persisting this dirty information so that we can limit the resource usage by not needing to keep everything in memory at any given point of time, and allowing us to actually come back up after the crash, detect what was actually dirty, what offset was last synced. And actually, the offset information is even better because persisting the last synced offset allows us to actually detect what data the client has actually synced successfully and allows us to recover up to that data. So the client can read up to that data, and the rest of the data can be up-replicated from any of the other successfully synced chunks written to any of the other disks, since it's pretty unlikely that this would happen on multiple disks at the same time. But obviously, one of the major issues with this is that there are performance challenges with this. Obviously, if you do have the dirty info, you need to be able to sync that to disk as well. And syncing that to disk in a performant manner is a challenge, and that's something that we had to work considerably on in order to align the syncs of our dirty info with the syncs of data and be able to rate limit that and manage that with our rate limiter. So I'll be handing over to Abhinav to go over an interesting case study for data integrity.
So as we discussed earlier, we have something called an inline checksum. So what we do is after every 4092 bytes of data, we embed a 4-byte CRC32C. And this becomes our first line of defense for data integrity. So even if you want to read a single byte of data from our file system, we will read 4096 bytes of data, and we will validate the data integrity by looking at the checksum and the 4092 bytes. So this is our first and most important line of defense against data corruption. But what we saw in the field was there were several instances of corruption that bypassed our inline checksum protection. So what we were actually seeing is that the inline checksums, the embedded CRC32Cs that we have in the data, they are correct. However, we are seeing the data is corrupted. And the way we were able to detect is because we have checksums at multiple layers. So we also have checksum at chunk layer, so at 32 MB boundary. And we saw that that particular chunk checksum is incorrect. So although our inline checksum, the embedded inline checksums were absolutely correct, the chunk checksum being incorrect gave us that information that there is something wrong with this chunk file. But because we have Reed-Solomon encoding for all our chunks and we have high data resilience, what we did was we recovered the chunk using the other healthy chunks. And then we started comparing the corrupted chunk with the recovered chunk to understand what is the corruption pattern. And what we see is something very interesting here. So if we look at the corrupt chunk versus the recovered chunk, we first see a 2-byte mismatch, followed by multiple zeros, so all zeros, and including the CRC32C itself, that is also 0. And the CRC32C is exactly matching the data. So somehow, this is a very interesting corruption pattern. And then after that, so this is the first block. So first block of corruption, and after that we have several blocks of 4096 blocks of corruption, where the data is completely uncorrelated to the actual data, but again the CRC32Cs are matching. And it was not a one-off rare instance. We saw several instances of this happening. So we decided to dig deep into it, like how this is happening and how our CRC32C, which is a pretty standard checksum algorithm, is getting beat, and how can corruption happen in this particular format that CRC32Cs are exactly matching. So what we did was we figure out there is a weird pattern in CRC32C. So let's say you have X bytes of data followed by 4 bytes of CRC32C of that particular X bytes, followed by all zeros, such that the length of data becomes 4092 bytes. The CRC32C of this particular 4092 bytes will always come out as 0. And we were also pretty surprised by it, but we wrote randomized unit test, and this supposedly holds true for any value of X. So this already gives us a hint on what's going on. So the client was able to write some, let's say, 10 bytes of data. And because the data was not full 4096 bytes, we added the CRC32C of those 10 bytes of data at that point, A1 line. And then supposedly something went wrong in the file system, due to which we were not able to write the full data. And the 000s that we are seeing, that are likely coming from Linux sparse, ext4 sparse file behavior. So let's look at the ext4 sparse file behavior. So ext4 has this sparse file behavior where if you write to a higher offset, you don't actually need to store the zeros. There would be holes, but you don't actually need to store these holes on the physical drive. You can just, the ext4 will actually just store some metadata information in the inode to indicate that there are holes. But the ext4 block size is 4096 bytes. So if you have even a single byte of write in the 4096 byte block, you have to do a physical allocation for the whole 4096 block, and you have to actually write zeros for that particular block. But for any subsequent blocks for which you haven't written any data, which are part of the ext4 whole, you don't need to do any physical allocation. So if you sort of combine this theory and look this in perspective to the corruption pattern that we are seeing, is that the zeros that are coming here are likely from the sparse file, ext4 sparse file, and this 4096 byte block was actually written to the disk, and these zeros were actually physically written. But the next blocks, the next 4096 byte block, we don't see any zeros, but we see some sort of random uncorrelated data. So how could that happen? So what we did was we looked into system logs to try to understand more why this corruption is happening. And what we found was that whenever we saw this corrupt file, we looked at the timestamps, the time point at which this file was being written to, and it perfectly correlated with the ext4 errors which we saw in syslogs. So our file system, our ext4 file system gets remounted to read-only mode if there are any disk errors. And this is a snapshot of the syslogs. And you can see that there are multiple failures in the syslogs we can see. There is even likely some sort of ext4 metadata corruption here as well. So what actually happened was that the client was able to successfully write a partial 4096 block with the inline checksum embedded. After this, the disk went to RO, and our file system was remounted to RO. So all of our writes after that particular point were never persisted to disk. But when the file system came back to regular read-write mode, our file system continued writing to that particular file, and we use pwrite to write to the file. So we started writing to a higher offset in the file, which actually succeeded, which sort of created this hole in the middle. The first block of corruption, where we have CRC32CS0, this went undetected because of this weird CRC32C behavior. And the subsequent blocks of corruption, which were supposed to be all zeros, they are actually pointing to stale data. So because they are pointing to some other previous file for which we have some data followed by CRC correct 32 CRC32C, and this is likely due to some ext4 metadata corruption, due to which instead of pointing to zeros, it is pointing to some stale data. So this was sort of a two-month-long investigation into the corruption issue and discovering these interesting behaviors about ext4 and CRC32C. So after this, we decided to improve our embedded inline checksum mechanism. And to improve it, we added some context to our inline checksum. So instead of just taking 4092 bytes of data and computing CRC32C of that, we add some context, which is the file ID as well as the offset in the file to the CRC32C. And adding this context ensures that first you cannot read the read on stale data would fail because the file IDs will not match even if you point to the stale data in some other file ID. And also even the zero CRC coincidence will not happen here because you are including the file offset in the file. So even that wouldn't happen. So this is how we improved our inline checksum mechanism after this corruption. So yeah, that's all we had. Any questions? Yeah.
When it comes to actual performance in the software-defined file system, you're essentially working with the same 2x2 node appliance that Mohinder at Nutanix started working on, brought it to Cohesity. Rubrik is very similar. And you've got 4 nodes, let's stay in the simple case. We're talking about the manually initialized write, say to a file system, and then a file system. So you're getting the most high priority write that you can deal with, and you've got 4 nodes.
Repeat that, summarize that question a bit. Oh, sorry. Just to summarize that question a bit, if I understand correctly. I'm going to summarize a bit and re-quote, correct me if I'm wrong. So basically, let's go over like a simple application that we have or a simple server that we have, which is 4 nodes. And some client, I think you mentioned Oracle is trying to write to our file system, say via NFS or something. and you're not getting the performance that you'd expect for whatever reason. How would we? What could we do to improve that?
What have you done, and what further can you do to improve the software-defined file system that has roots in the Google file system to Nutanix, now into Rubrik?
Right. So I guess the question, to repeat, what have we done? Kind of building off of the basic kind of Google file system or whatever the origins of our file system was to, and what can we do in the future to improve this, I believe. Yeah, so that's a great question. So I think one of the major ways we've done this is by kind of having this notion of IO priority. I think what that allows us to do is to ensure that all the bandwidth that we have available can be used for a job if that is determined to be the highest priority at that point in time. So if you have something that is the customer really cares about and they're really care about the performance at that point in time, we can all the bandwidth that we have available will be reserved for that job, and that will kind of maximize the value that you can get from the disk at that point in time. We also have several layers of caching, and obviously I think the trick here is with backup appliances in general, you always have to be kind of cost effective, right? And you usually have a lot more hard drives than you do have flash, and so very careful and intelligent use of flash, which allows us to kind of serve random data or random reads as well as possible. That I think helps us contribute to that as to help us do better as well. Does that answer your question? Yeah, perfect. Yeah.
So for that CRC error, is there a specific offset or something that this will happen? So,
This one?
Yeah. So you mentioned that for your unit test, you tried different combinations, such.
Yeah.
So is it always happening?
Yeah, it is always happening. X can be anything. It could be 1 byte, it could be 100 byte, it could be 500 bytes.
But the CRC is supposed to be able to adjust all the information and such.
Yes, it is able to, but it's not a completely random pattern. The X bytes of data, the first initial X bytes of data, they are completely random. But after that, you have 4 bytes of CRC32C of those X bytes of data, and then you have all zeros. So this particular pattern always gives you 0 CRC32C.
So you mean all 0 will yield 000 CRC32?
Yes.
It's not the previous one doesn't. It's not a problem.
No. So it is the CRC32C of all of this 4092 bytes of data, which includes random X bytes, followed by CRC32C of those X bytes, and then followed by all zeros.
Okay.
Yeah.
In your earlier slide, you mentioned there is a journal file which has offset and data. So does that mean you write data first to the journal file, later write it again to the final location?
Yes. So
Does that slow down the writes?
So what we do is when we are ingesting a backup, we'll first write to journal files. And this is important because journal files are just simple append-only offset, data, which is very optimized for writes. But this is not optimized for reads. And when we later merge it to our patch file, we want something that is read optimized. So we convert it into a patch file, which is sort of like SS table later. So there is some write amplification here because you first write to a journal file and then you convert it to a patch file. But overall, it is better because if you want to write it to a patch file online, it would be kind of tricky, and writing it in a sorted fashion wouldn't be possible because you can have data coming at any offset. So it is better to write it in a journal file and then later convert it to a patch file.
I have something to say to that as well. So I think one thing you mentioned, if I understand correctly, was does this affect our performance? So one thing is that because we deal with SLAs, and we have a job scheduling framework as well on top of the file system. One thing that we try to do best is that we have windows. We typically see windows where you have applications that write heavily, but you do have peacetime windows where there is no active I/O happening on the cluster from clients. So what we try to do is we try to maximize that peacetime window as much as possible to actually do all these optimizations, GC, any of the background activity that we have, to ensure that when clients are actually issuing I/O, they get as much bandwidth from the disk as possible. And that helps us, prevent, having any side effects to clients. And I also want to add that, in addition, there's a lot of algorithms here in terms of like fragmentation of the journal and how sequential the journals are, et cetera. And if the journal is good enough, or if the client actually has written the data in a read-friendly manner anyway, there's no need to do the transformation. So we have a bunch of algorithms to kind of make sure we don't do it blindly, to kind of make sure we're smart about it. So.
And for your patch file, is it LSM tree?
Yeah, so that's a good question. So the patch file, the entire structure does behave, yes, like LSM tree.
Okay. And does each node have a kind of LSM tree for the metadata? Is that right?
Yes. At a very high level, yes. Obviously, we don't want to go into the details since it's proprietary, but yeah, at a high level, yes.
So for each shard, when requests come in, how do you decide which shard to go to? Do you use a hash or do you use a range-based sharding?
Yeah, so when you have a read that comes in, we have a top-level index which allows you to determine whether the data is in a given patch file or not. But you do have this standard problem with a lot of LSM trees where you do have to traverse the tree per se to find where the data will lie. So that is a behavior that is there. So there are optimizations that we need to do in the background to ensure that your tree is of a reasonable size and depth to kind of control the length and the breadth of the tree.
I have a couple of questions. First is normally what I've seen is file systems tend to decouple checksum from the data. And mostly checksum is kept in the metadata traversal, and that's how location of data in checksum is separate. But in your case, you are keeping checksum with the data. And also, I think that this is a backup application, which means that majority of the reads and writes would be sequential and larger in size. So the follow-up question on that is, what are the cases where somebody would want to read 4K random reads? And the second question is, now because you are maintaining incremental diffs via patch files, there can be a situation where a lot of incremental diffs have happened and you end up having a long chain of patch files which would affect your read capability because you may be iterating all of it in worst case scenario.
Yes.
And is there a mechanism of flattening that chain also, and if yes, then when does that happen?
Yeah, so I think a lot of questions there. So I'll try to go one by one as much as possible. So you mentioned, I think, that different file systems try to decouple the checksum of the data, the checksums in the data, and try to put the checksum in the metadata layer. And that's something that we clearly haven't done. And the reason we want to do this is because we want to make it as easy as possible or as performant as possible to actually validate the checksums on every I/O, right? And one thing I think that you said after that is I believe that most applications, in a backup or data protection side is basically going to do sequential I/O, right, for reads or writes. And I think.
So then the question is, if that is the case, and that's the most common case, why are we maintaining checksums for 4K boundaries?
Right.
And what's the case wherein you have lots of random reads of 4K sizes?
Yes, so that's a great question. So one thing that Rubrik provides, a feature which is useful in cybersecurity events, is this thing called live mount, where you can actually materialize your application from the backup itself. And at that point in time, you're kind of dependent on whatever the application issues. And typically that can be random reads at any given size. And so that is something that we need to support, and that's the reason why we do this. So that answers the kind of 4K question. I do think you had another question, basically on the fact that going on the. Oh, yeah. So I think time's up, but we can chat later about this. Thanks. Yeah, thank you.